Hi everyone. In this lecture, we will learn about transpose of a matrix. It's a very important property of a matrix. How to calculate the transpose and what are different types of matrices related to transpose, which are symmetric matrix and skew symmetric matrix and their properties as well. So let's start. It's a very important topic again. Again in linear algebra, we will be seeing transpose of a matrix again and again. And another important property is inverse of a matrix that we will discuss later. So these two properties, transpose and inverse, will be like at least one question comes in exam from like one of these topics, and properties of transpose of a matrix basically. So let's start. It's a very easy concept in general. Like what it does, it will just rotate the matrix. So whenever you are taking the transpose of a matrix, essentially you are rotating it, which means the rows becomes columns and columns becomes rows. So if the matrix was m cross n before, the transpose of it will become n cross m, which means the number of rows will now become number of columns and number of columns will now become number of rows. So let's say A is a matrix of size m cross n. So A is a matrix of size m cross n, which means m is the number of rows and n is the number of columns in the matrix. Okay. Then the transpose of the matrix A, so A has the element Aij, okay. So the element in the ith row and jth column is denoted by Aij. Then the transpose is denoted by A transpose like this. So we denote it like this, A transpose, okay. And sometimes we denote it like this as well, like this, okay, just a dash. So both are okay. Transpose can be denoted like this. More general version is this one, okay. We most generally denoted using this one, A transpose. So here the ijth element, if the element in the ith row and jth column was Aij, it will become Aji here, okay. So what does it mean? So the element, let's say here in the second row and third column will become here the element in the third row and second column. That's what it will happen. So let's take an example and see how to calculate transpose. So here A is a matrix, okay. It is of size 2 rows and 3 columns. It contains 2 rows and 3 columns, okay. So A transpose will be a 3 cross 2 matrix, which means it will contain 3 rows and 2 columns now. So let's create 3 rows and 2 columns. Now let's look at this element. This element is present in first row and first column. So this element here will go in the first row and first column only. You will just swap the row number and column number of every element. So here it is first row and first column. Here also it will be in first row and first column. Now look at this element. This element is in second row and first column, right? So this 4 is in second row and first column. This is A21. A21, second row and first column. So this will become here in A transpose, it will become A12, which means first row and second column. Again you will swap. So 4 will go here. Similarly, this 2 will come here. This 5 will come here. This 3 will come here. And this 6 will come here, okay. So take any example, let's say this 5 was an element in second row and second column, so again it will become second row and second column element. If you take this element, this was in second row and third column, so now it will become third row and second column, which is this element, like that. So this is what transpose is. So essentially if you see, we just rotated the matrix 90 degrees. We just rotated the matrix 90 degrees. It's not just like a normal rotation, it's like rotation and flipping, okay. It's not a normal rotation actually. So don't go with the rotation exactly. Rotation is different, because if you rotate, 4 will come here, right? So it's not normal rotation, but it's sort of rotation and then flipping, okay, like that. So this is how we calculate transpose. Now here, let's say here B is a 2 cross 2 matrix, so there are 2 rows and 2 columns. So in B transpose also you will have 2 rows and 2 columns. So it will also be 2 cross 2 matrix. Now 1 will remain here, this minus 1 will go here, this 3 will come here, and this 2 will come here, okay. So all the rows are essentially becoming columns and columns are becoming rows. If you see carefully, this row, first row became the first column here, and the second row became the second column here. You can think of it that way as well. And similarly, the first column became the first row here, the first column became the first row here, the second column became the second row here, and the third column became the third row here. So rows becomes column and column becomes row. Here also if you see, the first row becomes the first column and second row becomes the second column, and first column becomes the first row and the second column becomes the second row, okay. So this is how transpose works. Transpose of a matrix is another matrix, okay? And very obviously you can see that transpose of a square matrix will be a square matrix. But transpose of a rectangular matrix will be a rectangular matrix. The number of rows and columns interchange. Okay, this is how we calculate transpose. So the element at ith row and jth column will become an element at jth row and ith column in the transpose. And if A is an m cross n matrix, then A transpose will be an n cross m matrix. Okay, the number of rows and columns will be swapped, the dimension. Okay, this is how we calculate the transpose of a matrix. Okay, now let's look at a few properties of transpose of a matrix. So we know that if matrix A is Aij, which means the ijth element is Aij, then in transpose it will become Aji, which means element in ith row and jth column will become the element in jth row and ith column in transpose. Now the first property is the transpose of transpose will become the same matrix again. It's a very simple property. So if you take a matrix and if you take its transpose, the element in Ij will become Ji, and similarly if you take the transpose of it again, if you take the transpose of this matrix again Aji will become Aij. Again Aji will become Aij, which is nothing but the matrix A. So if A is of dimension m cross n, A transpose will become n cross m, and if you again take the transpose, this will again become an m cross n matrix. Okay, this will again become an m cross n matrix and it will be the same matrix. We can take an example to prove this as well. So if A is the matrix, let's say 2 cross 3 matrix, 1, 2, 3, 4, 5, 6. Okay, this is a 2 cross 3 matrix. And if I take the transpose of it, it will become a 3 cross 2 matrix. So it will become 1, 4, 2, 5, 3, 6. And if you again take the transpose of it, you will get the same matrix back, which means again this first column will become the first row, which means 1, 2, 3, and the second column will become the second row, which means 4, 5, 6. Okay, so transpose of transpose becomes the same matrix again. Now the second property is A plus B transpose is equal to A transpose plus B transpose. It means that it is closed under addition. It is closed under addition, which means even if you take the addition, it will work. You just have to expand, or you can also say it is distributive over addition. So if you are taking the transpose of addition, it is just the addition of transpose. So A plus B transpose will become A transpose plus B transpose. Very simple. So if you want to prove it, let us say A is a matrix m cross n and the ijth element is Aij. Okay, then for it to be addable to B, if we are adding A and B, then B must also be of the same order, and hence B will also be of the same order, otherwise you cannot add them. So let's say the ijth element here will be Bij. Then A plus B transpose. A plus B transpose, A plus B will be again an m cross n matrix, right? And its ijth element will be Aij plus Bij. We already know this. The ijth element of A plus B will be Aij plus Bij. Now if you take the transpose of it, it will be an n cross m matrix, and the element will become, so here the ijth element is Aij plus Bij. This element will now become jith element. This element will now become jith element, which means it will become Aji plus Bji. Okay, the element here at Ij will become here element at Ji. So this is what will happen. And if you calculate the right hand side was A transpose plus B transpose. Very simple. The ijth element in A transpose will become Aji, and in B transpose it will become Bji. And if you add them all up, the ijth element will become Aji plus Bji, which is the same, which is essentially the same. And A transpose is also an n cross m matrix, and B transpose is an n cross m matrix, and hence A transpose plus B transpose is also an n cross m matrix, so order also is same. Again, if you don't get the feeling that way, you can take an example. So if again let's say A is the matrix 1 cross 3 matrix, let's say 1 cross 2 matrix, okay. So it contains two elements, 1 and minus 1, and B is also a 1 cross 2 matrix, let's say 3 and 4. Then A plus B will be what? It is also a 1 cross 2 matrix. You will add elements element by element, so 1 plus 3 becomes 4, minus 1 plus 4 becomes 3, and A plus B transpose becomes what? It is a 2 cross 1 matrix. So row will become column and column will become row. So it will become 4, 3. Now similarly, if you take A transpose will be a 2 cross 1 matrix and it will be 1 and minus 1. And B transpose will also be a 2 cross 1 matrix. It will be 3 and 4. And if you add these two, you will get the same matrix back. A transpose plus B transpose will also be a 2 cross 1 matrix. And it will be 1 plus 3, 4. And minus 1 plus 4 is 3. Okay, so it will be the same matrix as we got here. So A plus B transpose is A transpose plus B transpose. Okay, so this is the first property. Next is it is closed under scalar multiplication as well. So Ka times transpose, Ka transpose will be K times A transpose. It doesn't matter, you are multiplying with a scalar first or later, you will get the same answer. So very simple proof it also has. So how will we prove it? So let us say the ijth element in A is an m cross n matrix and the ijth element here is Aij. Okay. Then then if you take transpose, in A transpose, it will be an n cross m matrix and ijth element here will become the jith element here. Okay. And if you multiply it with K times A transpose will also be an n cross m matrix and its ijth element will become K times Aji. We already know this property, right? If you are multiplying with a scalar, every element multiplies by the same scalar. And similarly in the right hand side we had, this is the right hand side, in left hand side we had K times A whole transpose. So K times A will be what? K times A will also be an m cross n matrix and its ijth element will be K times Aij. K times Aij. Now this K times Aij will now become the jith element in the transpose. So if you take the transpose of this entire thing, it will become an n cross m matrix and this element will become the jith element. So K times A will become the jith element here and these two things are exactly same. Okay. So K times A is actually the jith element here in both of them. So it is closed under scalar multiplication and you can take an example very easily to prove it as well. I'll leave it for you as an homework. Take a matrix, multiply it with a scalar and you can prove it. Okay. Cool. So this is the third property and fourth is very important. The most important property here. What happens if you multiply two matrices? So AB transpose is equal to B transpose A transpose. AB transpose is not equal to A transpose B transpose. No. It is not distributive over matrix multiplication. No. Actually it is the other way around. So AB transpose will be equal to B transpose A transpose. Now how do we prove this? So let's try to prove it. The most important property here is AB transpose is equal to B transpose A transpose. Firstly, let us talk about dimensions. Okay. So if I say that A is an m cross n matrix, and let's say the ijth element of A is Aij. The ijth element of A is Aij. And now let us say that for B to be multipliable, so we know that A and B, we can multiply A and B only if the number of columns in A is equal to the number of rows in B. Then only you can compute AB. Right. So B must be an n cross P matrix. N cross P. It must have n rows. That's all. Number of columns we don't care. It must be an n cross P matrix. And let us say the jkth element here is bjk, which means the element in jth row and kth column is bjk, and here the element in ith row and jth column is aij. So this is what we have. Now if I talk about AB will be a m cross n and n cross m, and A is an m cross n and B is an n cross P matrix. So multiplication can happen, and AB will be, this and this are same, so AB will be an m cross P matrix. AB will be an m cross P matrix and its transpose. So AB transpose will be a P cross M matrix. It will be a P cross M matrix. Right. Now if I look at right hand side, B transpose will have the order of P cross N. right? Number of rows and columns interchange. And A transpose will have the order of n cross m. And notice that now we can multiply these two both. Now we can multiply these two both because these two are same, n and n are same here. You cannot multiply A transpose with B transpose because A transpose is n cross m and B transpose is P cross n. These two are not same. You cannot multiply them directly, and that is why it is B transpose A transpose, not A transpose B transpose. Okay, so it just swaps. These are not multipliable. This is incorrect. Okay, this is correct. So you can multiply them and now it will become P cross M matrix. So both are P cross M matrix. At least this thing is clear. Both are P cross M matrices, which means order wise we are good to go. Now we need to prove that all the elements are also same. So to do that, let us take any general element in AB transpose. So in AB, any general element, we know that let's say the product AB is P. The product AB is P. So any general element in AB will become PIK. The element in ith row and kth column will be summation for all j is equal to 1 to n. You will take the ith row of A and j you will take the ith row of A and kth column of B and multiply them element by element. So ith row of A, Aij times the kth column of B, which means Bjk. And this is what ikth element of P will be. This we have seen in the last lecture. And now this particular element, this entire element will be kith element of AB transpose. So in AB transpose, this entire thing will be the kith element, which means it will be in the kth row and ith column. Any element in kth row and ith column will look like this in the transpose. Right? Because in the normal, in the product, in the ith row and kth column we have this element. So in the transpose, in the kth row and ith column we will have this element. Okay, so in B transpose, A transpose, what will happen? Let's see. So in B transpose, any ijth element. So like B transpose, what will happen? If in B the element in jth row and kth column is Bjk, then in B transpose it will become Bkj. Right? It will become Bkj. Which is so essentially in B transpose, the element in jth row and kth column. In B transpose, the element in jth row and kth column will become Bkj, right? If here it was Bjk, here it will become Bkj. I hope this makes sense, right? In B transpose, the element in jth row and kth column will be Bkj here in B. In B it will be Bkj, right? So in B, whatever element was in kth row and jth column. And similarly for A transpose, the element here, if it is Aij, it will become Aji. It will become Aji, which means the element in ith row and jth column. The element in ith row and jth column, if here it was Aij, here it will be Aji. Here it will be Aji. So this is what will happen in B transpose and A transpose. Now if we have to multiply them both, so think about it. If we have to multiply them both, so firstly let us match the row and column number, right? Like as we did before, because we have to multiply this matrix with this matrix. So we will have to and both, like what is B transpose? B transpose is a P cross N matrix, and A transpose is an N cross M matrix. Okay, so we will have to multiply every row here and to every column here, element by element, a row here and a column here. Cool. So we will have to match these values. So let us take, let's say like here in B the element in B transpose, sorry, this is B transpose and this is A transpose. So in B transpose, the element in jth the element in kth row and jth column will become what? The element in kth row and jth column will become what? I am interested in that because I want to match the column number here and the row number here to make the multiplication possible. In B transpose, the element in kth row and jth column will become what? We will just swap it. So it will become Bjk, right? and in A transpose the element in jth row and ith column, the element in jth row and ith column will become what? Aij. I can write it this way as well. This is one way of writing transpose the ijth element. The other way of writing is like if in A the element in ith row and jth column is aij, then in A transpose the element in jth row and ith column is also aij. Right? Like think of it that way. And in B, if the element in jth row and kth column is bjk, then in B transpose the element in kth row and jth column will be bjk. This is another way of writing it. So in B transpose and A transpose this will happen. Now it is become simple because here the column number matches the row number here. That's what we want when we want to multiply B transpose into A transpose. So in B transpose A transpose what will happen? Let's say B transpose A transpose is a matrix Q. Then in Q the element in kth row and ith column, that's what we wanted, the element in kth row and ith column, right? We will take the kth row here, we already have the kth row here, and we will take the ith column here, we already have the ith column here. So the element in the kth row and ith column of B transpose multiplied with A transpose, so it will be summation j is equal to 1 to n, because the common element is n, and we have bjk times aij. So this is the element in kth row and ith column of B transpose A transpose, kth row and ith column. Here also we have kth row and ith column, and this was the element. And if you notice, these two are exactly same. Okay, so this was a complete proof of why A transpose B transpose is equal to, AB transpose is equal to B transpose A transpose with element by element mapping. But if you don't understand it completely, again, let us take an example so that it becomes easier. Let us try to do the same thing on an example so that you get the idea how is this happening. So you can, if you don't understand the proof, it is okay. But again, knowing the proof will help you in exam in many ways. If something else comes up, you'll be able to like get it easier, okay, without taking examples. So let us take an example and prove the same thing with an example. So if we have, let's say A is a matrix. Let's say A is a 2 cross 3 matrix. And A is, let's say 1, minus 1, 0. I like to add some zeros so that the multiplication becomes easier. Then you have 0, 2, 3, let's say. And B is, let's say 3 cross 1 matrix, so that the multiplication again is possible, because we want this value to be equal to this value. 3 cross 1 matrix means 3 rows and 1 column. So let's say 2, 1, minus 1, like that. Okay, so what will be the matrix AB? Matrix AB will be a 2 cross 1 matrix, which means it will have 2 rows and 1 column. The first row element will be this row multiplied by that column. So 2 ones are 2, minus 1 plus 0. 2 minus 1 is 1. And then in the second row we will have 0 into 2, 0, plus 2, minus 3. 2 minus 3 is minus 1. So this is AB. This is AB, okay? And hence AB transpose will be what? AB transpose will be a 1 cross 2 matrix, which is 1 and minus 1. This is what AB transpose will be. Now if you take B transpose A transpose, firstly B transpose is what? B transpose is a 1 cross 3 matrix. It will be 2, 1, minus 1. The column here will become the row here, times A transpose. A transpose is what? It is a 3 cross 2 matrix. It is a 3 cross 2 matrix, so it will contain 3 rows and 2 columns. Now it will become 1, 0. First column will become the first row, and minus 1, 2. And then we have 0, 3. So we'll multiply these two, 1 cross 3 times 3 cross 2, it will become a 1 cross 2 matrix. So B transpose A transpose will be a 1 cross 2 matrix. 1 cross 2 means 1 row and 2 columns, like this. Okay. So overall it will be a 1 cross 2 matrix, and the first element here will be, you multiply this row by this column. So 2 minus 1 and 0. So it will be 1. And then the second element will be 2 into 0, 0. Plus 2 into 1, 2, and then minus 1 into 3, minus 3. So 2 minus 3 is minus 1. So this is what B transpose A transpose is. So AB transpose is the same as B transpose A transpose. The order is also same and the elements are also same. So this is what happens. And here you can see that you cannot multiply A transpose B transpose. That is even not possible. and this is what will happen. And in general, this will keep on happening. You can prove this general statement as well. You can prove that A, B, C, D and so on transpose will be, let's say I can write it for A, B, C and like let's say, or let's take general like n matrices. A1 is a matrix, A2 is a matrix and so on. An is a matrix. Then the transpose of this entire product will be, you just do it in the reverse order. You will have An transpose, An minus 1 transpose and so on, A2, A1 like that. Okay. So you have to do it in the reverse order, A2 transpose, A1 transpose. So this is what will happen, and this is very easy to prove. You just have done it for 2 matrices. You can do it for multiple matrices as well. Okay, so this is what happens with transpose. If you are multiplying matrices and taking a transpose, when you are opening the bracket, you will have to do it in the reverse order. Okay. So this was the general theorem. These were some of the properties of transpose of a matrix, and we actually have seen detailed proof of each one of them as well. Cool. Now let us look at some types of matrices which are related to the transpose of matrix. So first one is symmetric matrix. So now we will see what symmetric matrix is. So a symmetric matrix is a square matrix. Okay, firstly it is a square matrix. A rectangular matrix cannot be symmetric. Just like a diagonal matrix or a scalar matrix or an identity matrix, a symmetric matrix has to be square, which means the number of rows and columns must be equal. So it is a square matrix that remains unchanged when its rows and columns are swapped. So which means that, what is swapping rows and columns? Swapping rows and columns means taking the transpose. Rows and columns are swapped means when transpose is taken. You can write it this way as well. Which means if a matrix remain unchanged after taking the transpose, then it is called a symmetric matrix. Okay, which means essentially A and A transpose must be same. They are exactly the same matrix. So if A transpose is equal to A, then A is a symmetric matrix. So there are two criteria. Firstly, A must be a square matrix, and second is A transpose must be equal to A. Actually, if you are writing the second criteria, first is anyways it must be happening, because let's say the order of A is m cross n. Let's say the order of A is m cross n. It is not squared, let's say. It is just m cross n. And if you are taking transpose of it will be n cross m. And if you are saying that these two matrices must be equal, for two matrices to be equal, their order must also be same. It must have same number of rows and columns, and all elements must be same, right? So m here must be equal to n and n here must be equal to m, which means that for two matrices to be equal, anyways m has to be equal to n, and hence A must be a square. So you don't need to write the first condition. If you are writing the second condition, which means A has to be equal to A transpose, then the matrix must be square. For a rectangular matrix, you cannot compare A and A transpose anyway, right? So it must be a square matrix, and A should be equal to A transpose. So even if you change rows and columns, it should not affect like the matrix should remain same. This is what a square symmetric matrix is. Okay, so let us see an example. Here we have a few examples. Are these symmetric matrices? So the first one is not even a square matrix, it is a 2 cross 3 matrix. A 2 cross 3 matrix or a rectangular matrix can never be symmetric. Okay, so it is not symmetric. It is not symmetric. And if you want, you can see as well, like A transpose will be what? A transpose will be a 3 cross 2 matrix, which is 1, 4, 2, 5, 3 and 6. So these two matrices are definitely not equal. Okay. Now if you look at B is a 2 cross 2 matrix, so it might be symmetric. For checking symmetricity, you have to take its transpose. So B transpose is also 2 cross 2, and it will be 1, minus 1, 3 and 2. 1, minus 1, 3 and 2. Now these two matrices, are they equal? No, because for matrices to be equal, all elements must be same. This one is equal to this one, but this 3 is not equal to this minus 1, right? And hence these two are not equal, and hence it is not symmetric. Okay, B is also not symmetric. A was also not symmetric. Now if we take a look at C, so C here is a 2 cross 2 matrix, and C transpose will also be a 2 cross 2 matrix. And if you write C transpose, it will become 1, 3 and then 3, 2. 1, 3 and then 3, 2. So if you look at it, these two matrices are exactly equal. They are exactly same. Every value is same. 1, 3, 3, 2. Okay, all the values are exactly same in the same position. And hence C is a symmetric matrix. Okay, C here is a symmetric matrix. Now if you take more examples, you will see like how symmetric matrices look. So if you take another matrix, let's say diagonal doesn't matter, you can have any element in diagonal, 3, 7, pi. Let's say any elements are there in diagonal doesn't matter. But the property which we have is, like, let's say if this is the principal diagonal, this is what the principal diagonal of a square matrix is, right? This way, where I is equal to j. So if this is the principal diagonal, this element must match this element, because we have said that A is equal to A transpose, and we know that the element at ith row and jth column in A is Aij, and this particular element is in A transpose is the element in jth row and ith column. In A transpose it is the element in jth row and ith column, and in A it is the element in ith row and jth column. Right. So, and we are saying that A and A transpose must be equal. So the element in the first row and second column in A, in transpose it will go in the second row and first column here. So this particular element will go here in transpose. This is what transpose does. And this particular element will go here in transpose. The element in the first row and the third row and first column will go in the third row and first column in the transpose. So this element will go here in transpose. And we are saying that this element must be equal to this element because A must be equal to A transpose, right? In A transpose, let's say what I am trying to say is, let us say in A this element is, let's say, small a, this element is small b, and this element is small c, and we don't care about these elements, let's say, for now. So in A transpose, what will happen? The diagonal in A transpose, the diagonal will remain as it is. Okay, anyways, in diagonal we don't care, because diagonal will remain as it is in A transpose as well, because the element in first row and first column will remain first row and first column here as well, second row and second column, second row and second column. So the diagonal will remain as it is. We don't need to worry about it. But this element here, A, it is in second row and first column, it will go here for first row and second column, and similarly B will go here and C will go here. And now we are saying that these two matrices must be equal. We don't care what here we have, but we are saying these two matrices must be equal. What does it mean? This element must be equal to A, this element must be equal to B, and this element must be equal to C. Which means this element and this element must be equal, and this element and this element must be equal, and then this element and this element must be equal. Then only the matrix will be symmetric. This is a symmetric matrix, whatever these elements are. Okay, so this is how symmetric matrices will look like. So in the same example, we can fill some values as well. Let's say 3, 7 and pi. If this element is -2, this element must also be -2. If this element is, let's say, E is a number, right? Or let's not take E, let's take -5. Then this element also must be -5. And this is 8, this also must be 8. So this is a symmetric matrix. If any one of the values was different, if this is -8, then it is not a symmetric matrix. But here right now it is a symmetric matrix, okay? So the number of independent numbers, independent means the ones which can change, are these many only. Because this must be equal to this must be equal to this, and this must be equal to this. So this entire part of the matrix is not independent. It is exactly equal to this entire part. Okay, and we will see this dependent independent property again, don't worry about it. So this is how symmetric matrices look like. Okay, the only property that you need to remember is A must be equal to A transpose, then A is a symmetric matrix. Now let us look at some properties of symmetric matrices. Okay, before that, let's look at the number of symmetric matrices. So what are they trying to say? For an n cross n symmetric matrix, the number of independent entries is n times n plus 1 by 2. So what does this statement mean? So what is an independent entry? Let's see that. So if I consider a 3 cross 3 matrix, or let's say we consider a 4 cross 4 matrix. A 4 cross 4 matrix will look like this thing. So we will have A11, A12, A13, A14, A21, A22, A23 and A24. Then A31, A41, A32, A42, A33, A43 and then A34 A4 4. This will be a 4 cross 4 matrix. Okay, a general 4 cross 4 matrix. This is how it will look like. And its transpose will look like something like this. This row will become a column. So A11, A21, A31, A41. Then this column will become this row. A12, A22, A23. Sorry, A22, A32 and A42. Then we will have A13, A23, A33, A43. The transpose will look like this. And A14, A24, A34 and A44. Okay. And if A is a symmetric matrix, A must be equal to A transpose. Which means these two matrices must be equal. Their order is anyways equal. They are both 4 cross 4 matrices. Now if you look at diagonal entries, they anyways match. We don't need to worry about diagonal entries. Diagonal elements are anyways matching because for them I is equal to j, and in transpose I becomes j and j becomes I. So they will anyways be diagonal elements and they will be exactly at the same position. So diagonal elements are independent. Diagonal elements are independent. It means that they can take any values. They can take any value and the criteria will satisfy because they will be in the correct position. Diagonal elements are independent. Now coming to non-diagonal elements. So the idea is all these values are actually equal to, if you take a look carefully, all these values are actually equal to these values. Right, because A21, if you notice carefully here, A21 is equal to A12, which means that these two values must be equal, and then this value must be, and A31 must be equal to A13 because these two matrices are equal, and hence we must say that A12 is A21 must be equal to A12 and A31 must be equal to A13 and A41 must be equal to A14 and A32 must be equal to A23 and A42 must be equal to A24 and A43 must be equal to A34. These conditions must satisfy. These 6 values will be equal to these 6 values. Okay, this value will be equal to this value, this value will be equal to this value, then this value must be equal to this value, this value must be equal to this value. So essentially it should be a mirror image. Like if you see the principal diagonal, this is the principal diagonal, it should be a mirror image. These values must be a mirror image of these values. Okay, then only the matrix will be symmetric, and hence not all of them are independent. If you notice here, only one of these values is independent, the other one must be equal to the other one, and hence except the diagonal elements. So how many diagonal elements were here in 4 cross 4 matrix? 4 diagonal elements were there. And out of the remaining elements, which means there were total 16 elements, there were total 16 entries in the matrix. Out of the 16, 4 are diagonal, remaining ones are 16 minus 4, which is 12. Out of the remaining 12, only half of them are independent, half of them are dependent on the remaining half. So out of the remaining 12, only half, which means 6 are independent and 6 are dependent. And hence total number of independent entries is 4 diagonal plus 6 non-diagonal, which is 10. Now same thing you can do for an n cross n matrix as well. For an n cross n matrix, there will be n diagonal elements, diagonal entries, and out of the remaining n square, total are n square entries. Out of the remaining n square entries, n of them are diagonal. So out of the remaining n square minus n entries, half of them are independent. So total number of independent entries will become n plus n square minus n by 2, which if you take LCM, it will become n square plus 2n minus n, which is n square plus n by 2, which is nothing but n plus 1 by 2. This is the number of independent entries in a symmetric matrix of size n cross n. Number of independent entries. The remaining n square minus n by 2 are dependent on the first half. Okay. So this is what is mentioned here. The total number of independent entries is n plus 1 by 2, out of which n are diagonal elements, they can take any value, and out of the remaining n square minus n elements, half of them are non-diagonal, which are independent. Okay. And the next point is, what is the number of symmetric matrices possible if we have k options for every entry? So this is also interesting. So what are they trying to say here? Let's say someone asks you how many, let's say there is a question, okay, how many symmetric matrices of size or dimension 4 cross 4 are possible if every entry can be a 0 or a 1. Okay, if every entry can be a 0 or a 1, then how many symmetric matrices are possible? Now we have already seen that they are saying that every entry in the matrix can be either a 0 or a 1. Now we have already seen a 4 cross 4 matrix will look like this, and only like we will have diagonal elements, so we will have liberty to take any value, and all these value, let's say, have liberty to take any value, and the remaining values are dependent. You don't have liberty because this value must match this value and so on. So the total number of independent entries in a 4 cross 4 matrix, we have already calculated it in the last slide. It is 10, like it is 4 diagonal plus, or you can directly use the formula n plus 1 by 2. So 4 into 4 plus 1 by 2, which will give you 10. So there are total 10 independent entries. Now each of these independent entry can take either a 0 or a 1, either a 0 or a 1, either a 0 or a 1. All these 10 entries can take a 0 or 1. Okay. So how many total possible combinations are there? By the rule of product, total number of different matrices, total number of symmetric matrices possible. These are also called binary matrices because they can take either value 0 or 1, Boolean matrices. Okay. So the total number of symmetric matrices possible will be 2 to the power 10 because every entry has two options. So 2 into 2 into 2, 10 times. These many different matrices will be possible. So there are 2 to the power 10 or 1024 different symmetric matrices possible of size 4 cross 4, where every entry can take two values, 0 or 1, let's say. And total number of matrices possible was 2 to the power n square, 2 to the power 16. There are total 2 to the power 16 matrices possible, right? Because every entry can take two values here. Out of them, 2 to the power 10 are symmetric and the remaining ones are not symmetric. Okay. So this is what a symmetric matrix is. Okay, and like this is how you can count the number of symmetric matrices, and this is what the exact same point is given. If we have k options for every entry, then the number of matrices possible will become k to the power n plus 1 by 2, because every entry can take one of the k values. So the number of matrices will be k into k into k. How many times? Number of independent entries times number of independent entries is n plus 1 by 2. So this is the number of symmetric matrices possible of size n cross n. Okay, if every entry can take n k different values. Okay, now let's see some properties of symmetric matrices. So the first property here is A plus A transpose is always symmetric. Okay, A plus A transpose is also always symmetric. Now what does this mean? So let us see the property. First is A plus, okay, A plus A transpose is always symmetric. Now when can you compute A plus A transpose? Okay, so for any matrix they are saying, so let's say A is an m cross n matrix, then A transpose will be an n cross m matrix, and you can compute A plus A transpose only if these two have the same order, because that is the property of addition. You can only add them if they have the same order, which means n has to be equal to m and m has to be equal to n. So basically you can compute okay, sorry, this is m cross n. So basically you can compute A plus A transpose only if m is equal to n, or for square matrices. So A plus A transpose is always symmetric for any square matrix A. So A must be a square matrix, otherwise A plus A transpose is not even possible. So for any square matrix A. Okay. So this is what the full property will be. Now let's say A is an n cross n matrix and A transpose will be an n cross n matrix, and A plus A transpose will also be an n cross n matrix. So if you have to prove this property, what we will do? It will be very simple. Like we can just compute A plus A transpose transpose. If I take the transpose of the entire matrix which is given. So A plus A transpose is the matrix given, and if I take the transpose of it, I'll get A transpose plus so I already know that A plus B transpose is A transpose plus B transpose, right? It is closed under addition, the transposes. So it will become A transpose plus A transpose transpose. Now A transpose transpose is nothing but matrix A itself. We have already seen this property as well. So this will just become A transpose plus A. And now matrix addition is commutative. You can write A plus B as B plus A as well. You can write it as A plus A transpose. Now we have just proved, let's say A plus A transpose is a matrix Q. We have just proved that Q transpose is equal to Q. It means that Q is symmetric. It means that A plus A transpose is symmetric. That's what we wanted to prove. Okay. Now you can take an example to verify the exact same thing. If I take any square matrix A, let's say A is 2, 3, minus 1 and 4. And if I just add it with its transpose will be 2, minus 1, 3 and 4. And if you add these two matrices, you will get 2 plus 2 is 4, 3 minus 1 is 2, minus 1 and 3 is 2, and 4 and 4 is 8. And this matrix is symmetric because these two values are same, diagonal elements don't matter. This matrix is symmetric, okay? And hence for any square matrix, A plus A transpose will be always symmetric. Cool. So we have proved this one. Now second is, if A is symmetric, then A to the power n is also symmetric. Okay. So what is it trying to say? The second property is saying that if A is symmetric, then A to the power n is also symmetric. Okay, so if you have to prove it, if A is a symmetric matrix, A must be a square matrix. Let's say A is of size n cross n, then A to the power n will be what? A to the power n will be A into A into A n times. Now all of them are n cross n matrices, so this will also become an n cross n matrix. Actually this n is different from this n. I hope you understand. Okay, so yep, like the entire matrix will also become n cross n. It will also be a square matrix. So now what do we want to prove? We want to prove that A to the power n is also symmetric. So if A is symmetric, we know that A transpose is equal to A, and if we calculate A to the power n transpose, it will just become A into A into A n times transpose. Now we already know that A, B, C transpose is, you open them in reverse order. Okay, in the transpose, if you have multiplication, you open them in reverse order. So it will become C transpose, B transpose, A transpose, like that. Okay, and since because of this property, I can write this one as A transpose into A transpose. Actually, they are all same only. So even in reverse order, it will look like same. So this will be n times. And we know that all of these A transposes are equal to A because A is symmetric. And hence I can write this as A into A into A into A n times, which is nothing but A to the power n. So we just proved that A to the power n transpose is equal to A to the power n, and therefore A to the power n is symmetric. Okay, we proved this one as well. Now if you want to take an example, we can take an example just to verify this thing. Let's take A as any symmetric matrix. If I take A as, let's say, 2, minus 1, 3 and 3, and if I take A square, if I compute A square, it will be 2, 3, 3 minus 1 times 2, 3, 3 minus 1. It will be just 4 plus 9, 13. Then you will have 6 minus 3, 3. Then you will have 6 minus 3, 3. And then you will have 9 plus 1, 10. So this is a symmetric matrix. Okay, a square is also symmetric. Now if you compute a cube also, it will also come out symmetric. A cube a to the power 4, you can compute it for any power, they will all come out to be symmetric matrices only. Okay, so if a is symmetric, any power of a will be symmetric. Okay, this is the property that we have proved. Now let's move to the next one. Next is sum of symmetric matrices is symmetric, and we have a scalar multiplication of a symmetric matrix is also symmetric. Now let's look at these two properties. So the next one is saying that sum of two symmetric matrices will be symmetric. What does it mean? It is trying to say that if A and B, okay, it is trying to say that if A and B are symmetric, then their sum is symmetric, then A plus B is also symmetric. That's what it is trying to say. Okay, if A and B are symmetric, then A plus B is symmetric. So if A is symmetric and B is symmetric, both have to be square matrices, and they cannot be of different order. They cannot be of different order because their addition must be possible. So their addition is only possible if they both have the same order, right? And anyways, if they are symmetric, they have to be square matrices. So they both must have same order, and A plus B will also have the same order, n cross n, sorry. A plus B will also have the same order, n cross n matrix, a square matrix. So if I want to prove this, so if A and B are symmetric, it means that A transpose is equal to A and B transpose is equal to B. These two things are given, and hence A plus B transpose will become what? A plus B transpose will become A transpose plus B transpose. That this thing we already know. And now A transpose is equal to A and B transpose is equal to B. We have already seen that. And therefore we can see that A plus B transpose is equal to A plus B, which means A plus B is symmetric. A plus B is symmetric. Now if you want, you can take an example to see this as well. Take two symmetric matrices of same order and add them. It will become symmetric. The next one was saying that scalar multiplication of a symmetric matrix is also symmetric, which means if A is symmetric, then Ka is also symmetric. If A is symmetric, K times the matrix is also symmetric. So if A is symmetric, let's say A is an n cross n matrix, and if A is an n cross n symmetric matrix, then A transpose will be equal to A, and now you have Ka. So if you take Ka transpose, it will just become, we know that Ka transpose is nothing but K times A transpose, and A transpose is A, so it will just become Ka. So we just proved that Ka is symmetric. Okay, Ka is symmetric, which means you multiply any matrix with any scalar and that will also be a symmetric matrix. Now based on these two properties, you can have some more properties, like, so if A is symmetric, K is symmetric, which means that if A is symmetric, minus A is also symmetric, because K can be minus 1 as well. If A is symmetric, then minus A will also become symmetric, and and we have also seen that A plus B is symmetric. So we can write it for A minus B as well. So if I calculate A minus B transpose, it will just become A plus minus B transpose. So it will just become A transpose plus minus B transpose. Now if a matrix is symmetric, negative of it is also symmetric. So if B is symmetric, then minus B is also symmetric, and I can write it as A plus minus B, which is nothing but A minus B. And hence A minus B transpose will also become A minus B. And hence if A and B are symmetric, A minus B is also symmetric. A plus B, A minus B, any multiplication. Actually you can write any factor, like any 3A plus 7B, all of them will be symmetric, okay, because of these two properties. You can just merge them. And essentially if this question comes in exam, you can just prove it this way. Take the transpose and try to see if it is equal to the original matrix or not. We have seen this like multiple times, right? And this is what we got so far, okay? So like this you can solve any question. Now the last property given is product of a symmetric matrix is also symmetric if and only if they are commutative, if and only if they commute. What do we mean by two matrices being commutative, or they are commuting? So two matrices are said to be commuting if their product is commuting, which means AB is equal to BA. We know that in general AB and BA are not equal. For any two matrices, I cannot say that AB is equal to BA. Even for square matrices of same order, I cannot always say that AB will be equal to BA. No, they might be different as well. Okay. And if AB is equal to BA, for some matrices AB will be equal to BA. Okay, for some of the matrices A and B, AB can be equal to BA. And if AB is equal to BA, we say that the matrices A and B commute. Okay, it is not always the case. A and B commute, and in some cases they might not. You just have to check that AB is equal to BA or not. So if AB is equal to BA, then only we can say that product of symmetric matrices is symmetric. So in general, product of symmetric matrices is not symmetric. We cannot say that if A is symmetric and B is symmetric, AB will also be symmetric. No. It will only happen if A and B commute, which means if AB is equal to BA, then only AB will also be symmetric. Why? Let us try to see the proof. So the theorem is saying that if A and B are symmetric, if A and B are symmetric, AB is also symmetric. AB is symmetric only under one condition, if and only if AB is equal to BA, otherwise it is not. If AB is not equal to BA, then you cannot say that AB will be a symmetric matrix. And if you want to see the proof, it will be very simple. If A and B are symmetric, A is, let's say, an n cross n matrix. For AB to exist, this value must be equal to this value. So this value must also be n, and if B is symmetric, B must also be a square matrix. So A and B must have the same order, and their product will also have same order, n cross n. So if A is symmetric, A transpose is equal to A, and B transpose is equal to B if B is symmetric, and hence AB transpose will be what? AB transpose will be equal to B transpose A transpose. Now B transpose is equal to B and A transpose is equal to A. So AB transpose is equal to BA. But for AB to be symmetric, AB transpose must be equal to AB, not BA, and hence BA must be equal to AB for AB to be symmetric. Then only you can say that AB will be symmetric. So only if this happens, then only AB will be symmetric, and vice versa. Okay. So it's not that always it will happen. Only if A and B commute, then only you can say that AB is a symmetric matrix. Otherwise it is not. Okay. So these were a few properties of symmetric matrices. Okay. Next we have skew symmetric matrix. They are also called anti-symmetric matrices. Okay. They are also called anti-symmetric matrices. Okay. So what is a skew symmetric matrix? It is also a square matrix, just like symmetric matrices. They also must be square, where the transpose is equal to the negative of the original matrix. The transpose is equal to the negative of the original matrix. In symmetric matrix, A transpose was equal to A. Here A transpose will be equal to minus A. Okay, it will be minus 1 into A. So if A is a square matrix and A transpose is equal to minus A, then A is a skew symmetric matrix. Note that the diagonal entries of a skew symmetric matrix must be 0. Okay. So why is it so? Let us try to see. So they are saying that for a skew symmetric matrix, A transpose must be equal to minus A. So firstly, you can only compare transpose and the matrix if it is a square. So write, yes, A and A transpose must be square. Let's say they are both n cross n. Okay. So what will A look like? What will A look like? So let's say I create a 2 cross 2 matrix. A11, A12, A21, A22. And this is the matrix A. Then A transpose will be A11, A21, first column will become the first row, and A12, A22. And minus of A transpose will be -1 into this matrix, which means you will multiply every value with -1. So minus of A transpose will be this matrix. It will just contain negative of all of these. And these two matrices must be equal, which means that A11 must be equal to minus of A11. And A21 must be equal to minus of A12, right? For this value and this value. And for A12 it should be equal to minus of A21, which is essentially the same thing. This will also give you the same thing. And then A22 will be equal to minus of A22. So if you look at diagonal entries, the condition becomes, for all diagonal elements D, you will have D is equal to minus D, which means that 2D must be 0, which means that every diagonal entry must be 0. Every diagonal element must be 0 if D is of form AII, which means if D is a diagonal entry where row number is equal to column number, you will have a condition like this, because AIJ will be equal to minus of AJI. If I and I are equal, generally speaking, you will have AII is equal to minus of AII, and therefore every diagonal entry must be 0 in a skew symmetric matrix. You cannot have any other value. These values must be 0. Otherwise, they cannot be equal to the negative of themselves, right? And for the remaining entries, you can have anything. Let's say if this is 3, this can be minus 3, right? So this will be a skew symmetric matrix like this. Let's say these two elements are 0, and if this element is 3, this element must be minus 3. Here also same thing will happen. If this is A, this will be minus A. In symmetric matrix, these must be equal, but here you will have opposite sign. And similarly for a 3 cross 3 matrix, these 3 elements must be 0, and let's say if this element is 5, this element must be minus 5. If this element is minus of pi, then this element must be equal to pi, which means negative sign, right? So this and this element are like, it's again a mirror image along the primary axis, but the negative sign will be there. And in the primary diagonal, you will have zeros. So if this element is 3, this element must be minus 3. Then this will be a skew symmetric matrix. Yeah, you can check. Okay. So this is what happens for diagonal elements must be 0, and for any other Aij will be equal to minus of Aji for non-diagonal elements. Okay. Cool. So this is what skew symmetric matrix is. Again, note the fact that diagonal entries of a skew symmetric matrix must be 0. They are not independent. They must be 0. All of them will be 0. Then only the matrix can be skew symmetric. Now here we have a few examples again. So obviously A is a rectangular matrix. It is a 2 cross 3 matrix. It cannot be skew symmetric. It cannot be skew symmetric. Even if you check A transpose, you will get 1, 4, 2, 5, 3, 6. Definitely A is not equal to minus of A transpose, or A transpose is not equal to minus of A. No. Here in this case, diagonal elements are not 0. So anyway, this cannot happen. So this is also not. Even if you calculate B transpose, it will contain 1 minus 3 and then 3 2. So this matrix is not negative of this matrix, because even if you say minus B is minus 1, minus 3, 3 and 2. So they are not equal. Now here in C, diagonal elements are 0, and for the remaining elements they are just opposite sign. So this is a skew symmetric matrix. If you check C transpose, you will get 0, minus 3, 3 and 0. And if you see minus C, then it will also be 0, minus 3 and 3 and 0. They are both equal, and hence C is a skew symmetric matrix here. Okay. So this is how you can just check a matrix is skew symmetric or not. Now moving on to the number of skew symmetric matrices possible. How many independent entries are there in an n cross n skew symmetric matrix? So if you have an n cross n skew symmetric matrix, let's say there is a matrix A, it is n cross n. Again, let's say it is 4 cross 4. A21, A22, A23, A24, A31, A32, A33, A34, and then A41, A42, A43, A44. This is the matrix A. It is of size 4 cross 4. Then its transpose. Then negative of A. Then negative of A will be what? It will just have negative of all the values. This will be minus A. and A transpose should be equal to minus A. What is A transpose? The transpose of A, which means A11, A21, A31, A41, A12, 22, 32, 42, then 13, 23, 33, 43, then 14, 24, 34, 44. Okay, so this will be A transpose, and these matrices must be equal. These matrices must be equal. So if for a 4 cross 4 matrix, the matrix was Aij, then I have just created a minus A and A transpose. These matrices must be equal. So for the diagonal elements, we have already seen diagonal elements must be 0. The reason is A minus of A11 should be equal to A11, and same for A22, 33 and 44. Okay, and hence all these values must be equal to 0, otherwise this cannot happen. Okay, and therefore A11 and A22 and A33 and A44 must be 0. These values must be 0. So they are not independent. They are not independent. They cannot just take any value. These values must be zeros. Then only this can happen. So diagonal elements are not independent. Now, if the entry is not a diagonal entry, then what will happen? We will have minus of A21 will be equal to A12. So we just got that A12 should be equal to minus of A21, and similarly A13 is minus of A31. They must be of opposite sign, and A14 must be equal to minus of A41, and A23 must be minus of A32, and A24 must be minus of A42, and A34 must be equal to minus of A43. These 6 conditions we will have. So out of the remaining 12 entries, 16 minus 4 is 12. Only half of them are independent, which means only 6 entries are independent. Here even diagonal entries are not independent. You just have choice for these 6 values, because the remaining 6 values must be a mirror image with a negative sign. Then only it will be a skew symmetric matrix. And same for an n cross n matrix, you can say that diagonal elements are not independent, and out of the remaining n square minus n entries, n square are total entries, n are diagonal entries, half of them are independent. So total number of independent entries will be n minus 1 by 2. For symmetric matrix it was n plus 1 by 2. Here it is n minus 1 by 2. So the number of independent entries is n minus 1 by 2, and if we have k options for every entry, we have already seen it in symmetric matrix, we just raise it to the power k. So let's say if we have to find how many skew symmetric matrices of order 4 are possible. So of order 4, we have only 6 possible independent entries, right? And hence the number of skew symmetric matrix, if every element can be either 0 or 1, will be 2 to the power 6. And here it will be k to the power n minus 1 by 2. Okay, so it is exactly the same proof as we did in symmetric matrix. Same thing you can follow for a skew symmetric matrix as well. I'll leave this proof as a homework for you. You can do it on your own. Cool. So these are the number of skew symmetric matrices. Now let's see a few properties of skew symmetric matrix. Okay, so the first property we have here is A minus A transpose is always skew symmetric. Okay, so again, how do we prove it? Just like symmetric matrices, we can prove it. So the first property is A minus A transpose is always skew symmetric. Now again, you can compute A minus A transpose if and only if A is a square matrix, right? Because otherwise you cannot subtract A from A transpose. So for any square matrix A, just like we did it in symmetric matrix, here also for any square matrix A minus A transpose will always be skew symmetric here. A plus A transpose is always symmetric, A minus A transpose is always skew symmetric. How? So let's say A is a n cross n matrix, and A minus A transpose will be what? We are not assuming here that A is symmetric or skew symmetric. We are saying that for any square matrix A minus A transpose should be skew symmetric. So if I take the transpose of it, it will just become A transpose minus A transpose transpose. which is nothing but A transpose minus A, because A transpose is A, which is nothing but minus 1. If you multiply minus 1 through all of it, it will just become minus of A minus A transpose. So if you take A minus A transpose as Q, you just prove that Q transpose is equal to minus of Q. It means that A minus A transpose is skew symmetric. It is skew symmetric, okay? And if you take an example, you can see it as well. Let's take any skew symmetric matrix. These elements must be 0. This element is minus 3 and this is 3, let's say. Then A minus A transpose here will be 0, 3, minus 3, 0, minus the transpose of it. The transpose of it is 0, minus 3, 3 and 0. So it will just become 0, 0. Then 3 plus 3 is 6 and minus 3 is minus 6. So you can see that it is skew symmetric. Actually, in this example, I took A as a skew symmetric matrix. Even if A is not a skew symmetric matrix, this theorem is for any square matrix. So let us take any square matrix and prove it as well. So if I take, let's say, A as 5, minus 3, 6 and 2. And if I subtract its transpose will be 5, 6, minus 3 and 2. For any square matrix A minus A transpose, let's say this is A, then this will be A transpose. And even for this will happen. So 0, 5 minus 5 is 0, minus 3 minus 6 is minus 3 minus 6 is minus 9, and then 6 minus 3 is 9, then 2 minus 2 is 0. So this is again skew symmetric, okay, because this 2 are minus and diagonal elements are 0. So for any square matrix A minus A transpose will be skew symmetric and A plus A transpose will be symmetric. Now next is sum of skew symmetric matrices is always skew symmetric, and scalar multiplication of skew symmetric matrix is also skew symmetric. So just like symmetric, addition and scalar multiplication will hold true for skew symmetric matrices as well. So if A and B are skew symmetric, let's say, if A and B are skew symmetric, so let's say A is n cross n and B is also n cross n, then A plus B transpose will be equal to what? It will be A transpose plus B transpose. Now if A and B are symmetric, A transpose will be equal to A and B transpose will be equal to B, and hence A transpose, if A and B are skew symmetric, then A transpose will be equal to minus A and B transpose will be equal to minus B, right, by the definition of skew symmetricity. And you can write, see, actually for skew symmetricity you can write it like this as well. A plus A transpose is equal to 0. If you take A this side, it will just become 0 matrix. You can write it like this as well, skew symmetricity. B plus B transpose is equal to 0. Okay, this is another way of writing skew symmetricity. Okay, that's all. So A transpose will be equal to minus A and B transpose will be equal to minus B. So it is just minus A minus B. So if you take minus 1 out, it will become minus of A plus B. So we just proved that A plus B transpose is minus of A plus B, and hence A plus B is skew symmetric. And same for scalar multiplication, you will have Ka transpose. Ka transpose will be K times A transpose, and A transpose is minus A, so K times minus A, so it will just become minus of Ka, and therefore Ka is also skew symmetric. And because of these two properties, now again you can claim different things for A minus B and so on. Okay, so just like symmetricity, skew symmetricity is also closed under addition and scalar multiplication. Okay, cool. Now coming to the last property of skew symmetric matrices, if A is symmetric, then A to the power n. So if A is skew symmetric, okay, this is wrong, this must be, if A is skew symmetric or anti-symmetric, then A to the power n is skew symmetric if n is odd and symmetric if n is even. So we already know that if A is symmetric, then A to the power n is always symmetric. But if A is skew symmetric, then A to the power n can be anything. It depends on n, if it is even or odd. So how do we prove it? So the statement is if A is skew symmetric. Then a to the power n is symmetric if n is even, and skew symmetric if n is odd. Okay, this is the statement, and it is very easy to prove. So if you have to see the proof, so if A is skew symmetric, you can say that A transpose will be equal to minus A, and hence A to the power n transpose will be equal to A times A transpose, which is here A is n times. So it will just become A transpose times A transpose, because in product it just opens backwards. So this will be A transpose into A transpose like this n times. Okay, so this thing is the same proof we have seen for symmetric matrices as well. Now this A transpose will become minus A, so it will just become minus A into minus A and so on, minus A n times. Now in the property of scalar multiplication, we have seen that you can take all the scalars together. It doesn't matter in which order you are multiplying the scalars. This thing we have seen in the first lecture, right? Whenever you are multiplying a matrix by a scalar, you can just do them together. It is associative. So you can take all these minus ones together in the front. So this will just become minus 1 into minus 1 n times. So minus 1 to the power n. Then you will have a n times. So it will become minus 1 to the power n, a to the power n. So this is what you have. So a to the power n transpose becomes minus 1 to the power n, a to the power n. So essentially it depends. So a to the power n transpose will become, if n is even, minus 1 to the power n will become 1. If n is even, minus 1 to the power n will become 1, and hence it will become a to the power n if n is even. And if n is odd, minus 1 to the power n becomes minus 1. So it will become minus a to the power n if n is odd. And hence if n is even, a to the power n transpose becomes a to the power n, which means a to the power n becomes symmetric. This is symmetric because a transpose is equal to a is symmetric. And if n is odd, then a to the power n transpose becomes minus of a to the power n, which means it becomes anti-symmetric or skew symmetric. And that's what you wanted to prove. Okay, that's what you wanted to prove. If n is even, it is symmetric, and if n is odd, a to the power n is skew symmetric. So you can see an example of this as well if you want. So if you take any skew symmetric matrix A, let's say 0, 0, minus 2, 2. So A square will be symmetric. A square will be symmetric. It will be 0, 2, minus 2, 2, 0. So it will be 0, minus 4, then 0. Okay, 0 and minus 4, yeah. 0 and 0, 0. Then it will be 0 and 0, 0. Minus 4 and 0, minus 4. So you can see it is symmetric. It is not skew symmetric, it is symmetric. Okay, because these two elements are equal, we don't care about diagonal elements. And if you compute a cube, it must be skew symmetric. So it will be this times a, 0, 2, minus 2, 0. So it will become minus 4 and 0. 0 and 0 is 0. Then minus 8 and 0 is minus 8. Then 0 and 8 is 8. Then 0 and 0 is 0. So here you can see it is a skew symmetric matrix. Okay, it is a skew symmetric matrix. So a square will be symmetric, a cube will be skew symmetric, and again a to the power 4 will be symmetric, a to the power 5 will be skew symmetric, and so on. It will just go on. Whenever you raise it to odd power, it will become skew symmetric. Whenever you raise it to even power, it will become symmetric automatically. And if a was symmetric, this is very strange. If a had been symmetric, then all the powers are symmetric. We have already seen that. But for skew symmetric, it becomes alternatively it becomes symmetric and skew symmetric. Okay. Cool. So these were a few properties on skew symmetric matrices. Now let's see some more properties. So we have one more property of transpose of a matrix. Let's see that. Okay, so the next property is any square matrix can be represented or expressed as the sum of a symmetric and a skew symmetric matrix. So you can represent any square matrix as a sum of a symmetric matrix and a skew symmetric matrix, and that's very simple because we have seen that for any square matrix A, A plus A transpose is always symmetric for any square matrix, right? We have seen this. And we have also seen that A minus A transpose is always skew symmetric. It is always skew symmetric. And if A plus A transpose is symmetric, then half of A plus A transpose will always be also be symmetric because of scalar multiplication. For any symmetric matrix, if you multiply it by a scalar, which here the scalar is 0.5, scalar can be anything. So half of A plus A transpose should also be symmetric. And similarly, for scalar multiplication on skew symmetric matrices, we have seen that if A is skew symmetric, K times A is also skew symmetric. Again, half of A minus A transpose will be skew symmetric. And if you add these two matrices, if you add half of A plus A transpose and half of A minus A transpose, then you will get half A plus half A is A, and half of A transpose minus half of A transpose will go away. You will just get A. And hence you can write any matrix A as A plus A transpose by 2. This will always be a symmetric matrix. And you can write A minus A transpose by 2. It will always be a skew symmetric matrix. And if you sum these two, you will get A. So you can always represent any square matrix can be expressed as a sum of a symmetric and a skew symmetric matrix. This is pretty simple, right? And if you want to solve an example, let's say if I take a matrix 5, or let's take 5 minus 6, 4 and 8. Let's say this is our matrix, okay? Then this is our matrix A, 2 cross 2 matrix. Then if I write what is half A plus A transpose? So A plus A transpose will be 5, 4, minus 6, 8 plus A transpose will be 5, minus 6, 4, 8. And we will take half of this entire thing, half of this entire matrix. So it will just become 5 and 5 is 10 and half of it is 5. 4 and minus 6 is minus 2 and minus 2's half is minus 1. Then minus 6 and 4 is again minus 2, minus 2's half is minus 1. And then 8 and 8 is 16 and half of that is 8 again. So it will just become 5 minus 1, minus 1, 8, which is a symmetric matrix, which had to be a symmetric matrix. And if you compute half of A minus A transpose, so it will become half of A is 5, 4, minus 6, 8, and minus the transpose of it, 5, minus 6, 4 and 8. So it will become 5 minus 5 is 0. So the first element will become 0, and then 4 minus 6. 4 minus 6 is 4 plus 6. 10 by 2 is 5. Then minus 6 minus 4 is again minus 10 by 2 is minus 5. And then 8 minus 8 is 0. So 0 by 2 is 0. And you can see that this is a skew symmetric matrix. So I have actually found a symmetric matrix and a skew symmetric matrix whose sum, let's say this matrix is P and let's say this matrix is Q. Then you can check very easily that P plus Q here will again give you A, which means 5 plus 0 is 5, minus 1 and 5 is 4, then minus 1 and minus 5 is minus 6, and 8 plus 0 is 8, which gave you the same matrix A again. So we have actually broken A into as a sum of a symmetric matrix and a skew symmetric matrix, and you can do this for any square matrix. So any square matrix A can be represented as a sum of a symmetric matrix and a skew symmetric matrix using this property that A plus A transpose is symmetric and A minus A transpose is always skew symmetric. Okay. Okay, cool. Now let's look at some examples on transpose of a matrix and symmetric and skew symmetric matrices. If A and B are symmetric matrices of same order, then AB minus BA is. A and B are given as symmetric matrices, which means A transpose is equal to A and B transpose is given as B, and they are of same order. Let's say both are n cross n, A and B. Then AB minus BA. What will happen to AB minus BA? They are asking, is it a symmetric matrix? It is a skew symmetric matrix. Is it a zero matrix or is it an identity matrix? See, zero and identity definitely we don't know. AB minus BA can be anything right now. So we cannot say that it is zero or identity. It is a zero matrix if they commute. If they commute, AB will be equal to BA and hence AB minus BA will be 0. But they are not saying that A and B commute. If A and B commute, then it would have been a zero matrix. Identity also we cannot say. So we will have to make a comment on symmetric and skew symmetric. For that we will just take the transpose of it and we will know. So the transpose of it will be AB transpose minus BA transpose. Now AB transpose is nothing but B transpose A transpose, and BA transpose is nothing but A transpose B transpose, right? Because it expands in reverse order. Now B transpose is B and A transpose is A, and A transpose is A and B transpose is B. So it became BA minus AB, which is nothing but minus of AB minus BA, which is nothing but minus of AB minus BA. So if we take AB minus BA as Q, we just figured out that Q transpose is equal to minus of Q. It means that Q is anti-symmetric or skew symmetric, which means that AB minus BA must be skew symmetric in nature. It must be skew symmetric. It is not symmetric. It must be skew symmetric. So if A and B are symmetric, AB minus BA is skew symmetric. We found one more property. Okay. So anything like this can come in exam. You just have to take transpose and figure out. It will be very easy. Cool. So it is skew symmetric. Now moving on to the next example, let A is equal to cos alpha minus sin alpha cos alpha. This is a standard transformation matrix. We will see this later. Okay, it just rotates any vector by angle. Okay. So and suppose that A plus A transpose is given as I. Here we are given that A plus A transpose is I, where I is the identity matrix. And if alpha is equal to k pi, find the minimum positive value of k. Cool, let's try to see. A plus A transpose is given as I. What is A plus A transpose? It is cos alpha, sin alpha, minus sin alpha, then cos alpha. This is A. And A transpose is cos alpha, sin alpha, minus sin alpha, then cos alpha. And if you sum these both up, you will get cos alpha plus cos alpha is 2 cos alpha, minus sin alpha plus sin alpha is 0, sin alpha minus sin alpha is 0, and then cos alpha plus cos alpha is 2 cos alpha again. So, and this particular A plus A transpose is given as an identity matrix. This is given that this is an identity matrix. Identity matrix is what? It is 1, 0, 0, 1. And therefore you can see that both these values, 2 cos alpha here and 2 cos alpha here, both of them have to be 1. It means that 2 cos alpha must be equal to 1. It means that cos alpha must be half. Cos alpha must be half. What is the value of alpha? Okay, so cos alpha must be half, and we have and they are saying that if alpha is equal to k times pi, then what is the minimum positive values of k? Positive value of k. So cos alpha is half for what? Pi by 3. Right, and then you can keep adding all schools per, yeah, or you can keep adding like pi to it, like pi by 3, and then like the next value might be, you can add 2 pi as well, right? Like it is periodic. It is definitely periodic. Cos alpha looks like this, right? Cos alpha looks like this, and we are finding cos alpha is equal to half. So it must be half like this at these values. So first one is pi by 3, then second one will be 2 pi minus pi by 3, then the next one will be 2 pi plus pi by 3, So pi by 3, 5 pi by 3, then 2 pi plus pi by 3, which means 7 pi by 3, and so on. There are multiple values. So k can be 1 by 3, 5 by 3, 7 by 3, and so on. It can be multiple values, but we have to find the minimum positive value. Minimum positive value of k will become 1 by 3. The minimum possible alpha is pi by 3, and hence the minimum possible value of k, this is given to be k times pi. So minimum positive value of k is 1 by 3. Okay, that's what we want. The minimum positive value of k should be 1 by 3 or 0.33. Okay, so this is how you can solve this question. Cool. So the answer is 0.33, which is 1 by 3. So yes, like this is all about transpose of a matrix and skew symmetric matrix and symmetric matrix, and we have seen lots and lots of properties of both of them. So yeah, like just see the logic, like how we are actually proving the different properties. The same logic you can apply to any type of problem and you'll be able to solve it in the exam. Okay, so thanks a lot for watching this lecture. In the next lecture we will see more special matrices, different like singleton and idempotent, nilpotent, involutory, and the properties of these matrices as well, and that will conclude the matrix part. Okay, so yeah, thanks again, and let's meet in the next lecture. Bye bye.